What happens if you keep slowing down by Veritasium, 30 minutes. There's a video of light traveling through a bottle at 250 billion frames per second. Then the camera starts moving, sweeping across the scene faster than the laser pulse itself. A camera moving faster than light. It sounds impossible, but by the end of this video you will understand exactly how it works, and you will have seen something even more extraordinary. A movie of electrons moving around molecules, captured at over a quadrillion frames per second. In the 1920s, MIT engineer Harold "Doc" Edgerton was trying to figure out why electric motors behaved unpredictably during power surges. The problem was simple but unsolvable. The machines spun too fast for the human eye to see, and cameras of the era were too slow to capture anything but blur. Then, Edgerton noticed that his equipment gave off bright flashes during surges, and in those split-second flashes, the spinning motors appeared frozen solid. He built on this insight to create the modern strobe, a device that loaded electrons onto a capacitor and then discharged them through a xenon gas tube, heating it to 10,000 Kelvin, nearly twice as hot as the surface of the sun, producing a flash lasting just 10 microseconds. By the early 1930s, Edgerton was packing his strobe into his car and pulling into random factories, cold calling the president to ask if they had any motors that did not work right. But it was his wife's complaint that changed everything. After seeing his 300th photo of a synchronous motor, she told him, "Harold, can you take a picture of something a little more interesting?" And so he did. Tennis balls pancaked against rackets, hummingbirds frozen mid-flight, bullets ripping through playing cards. These images, published in Life magazine and National Geographic, were essentially the social media content of the 1930s, and they revealed a hidden world existing in the microseconds between moments. Taking a photo in a 10 millionth of a second is impressive, but the real engineering challenge is timing. How do you get a strobe to fire at precisely the right half-millionth of a second when a racket hits a tennis ball? The answer is sound. A microphone picks up the sharp sound of the event, a pop, a crack, a gunshot, and triggers the strobe with a tiny delay. The video team recreated Edgerton's setup, popping a balloon in a darkened room with the camera shutter left open. When the pop hit the microphone, the strobe fired for 100,000th of a second, capturing the balloon mid-explosion with stunning clarity. You can see inside the balloon in the resulting image. They even shot a bullet through a playing card using both a modern 20,000 FPS slow-motion camera and Edgerton's strobe technique side by side. The strobe photo from a technique invented in the 1930s is dramatically sharper than the modern camera footage. The reason comes down to two types of resolution: spatial resolution, how many pixels, and temporal resolution, how many frames. Hardware forces you to trade one for the other. Edgerton's approach goes all in on spatial resolution with just a single perfect frame, while slow-motion cameras sacrifice pixel count for frame rate. Edgerton's strobe attracted unexpected attention from the military. In 1939, U.S. Major George Goddard walked into Edgerton's lab unannounced. The military needed a safer way to photograph enemy positions from the air at night. The old method involved dropping a parachute flare and then flying underneath it, completely exposed and silhouetted against the light. Goddard asked Edgerton if he could build a strobe powerful enough to illuminate the ground from a mile up. Edgerton did some calculations and said yes. The resulting flash released 60,000 joules in a single millisecond, a peak power of roughly 60 megawatts comparable to the output of a large solar farm. This flash was used the night before D-Day, allowing the Allies to photograph Normandy and confirm that German troops were unprepared for the attack. A strobe, born from curiosity about electric motors, ended up helping to win World War II. Push temporal resolution to its extreme, and you can only read 1 pixel at a time. But that 1 pixel can count photons at nearly a trillion frames per second, with each frame lasting roughly 1 picosecond. In that time, light itself travels only 0.3 millimeters. This technology already exists in many smartphones as LiDAR. To film light traveling through a scene, researchers at the University of Toronto and MIT set up a scaled-down room with objects like cones, spheres, and mirrors. A short laser pulse hits one point, photons scatter everywhere, and the single-pixel camera records how many photons arrive from just one position. Then the camera moves slightly and the experiment repeats, hundreds of times, pixel by pixel. The key requirement is that the scene plays out identically every time, because each pixel comes from a different run of the experiment. Stitch all the single pixel recordings together, and you get a full video of light propagating through a scene. You can watch wavefronts form below a bottle, see light bounce off a mirror in a fish tank, watch a diffraction grating split light into its different modes. By recording from multiple angles and stitching the views together, researchers can even create fly-through visualizations, where the virtual camera moves faster than the light pulse itself, which is why the opening clip appears to show a camera moving faster than light. Combine both extremes of strobe photography, the single-frame sharpness of Edgerton's technique and the trillion FPS temporal resolution, and you arrive at something almost unimaginable, a camera for electrons. At SLAC National Lab, a perfectly straight electron accelerator stretches 3.2 kilometers. Electron pulses are accelerated to 99.9999992% the speed of light and sent through undulators, stacks of alternating magnets that cause the electrons to wiggle. Because the electrons are relativistic, length contraction compresses the wiggling wavelength down to the X-ray regime. The electrons bunch into parallel sheets spaced exactly one X-ray wavelength apart, emitting coherent laser pulses as short as a few hundred attosecond. An attosecond is to a second what a second is to the age of the universe. These ultra-short X-ray pulses are the molecular equivalent of Edgerton's strobe. To study a molecule, researchers first hit it with a conventional laser to trigger some dynamic process. Then, after a precisely controlled delay, the X-ray pulse ejects a core electron from a specific atom within the molecule. By measuring the kinetic energy of that ejected electron, scientists can infer the electron density around that atom at that exact moment. By repeating this with slightly different time delays, each one a few hundred attoseconds apart, they build up a frame-by-frame movie of how electron density changes inside a molecule. This is effectively a quadrillion frames per second movie of the fundamental forces that govern all of chemistry. The researchers at SLAC make a profound point about why this matters. Electrons create the fields in which everything else happens. Molecular bonds break and form because electrons give them a push. Being able to look into their motion is the most fundamental way of studying materials and matter. The video shows a simulation, validated by experimental data, of a molecule called paraminophenol having an electron removed. Red regions show increasing electron density, blue regions show decreasing density, and you can watch charge distribution literally flowing across the molecule in real time. The simulation matches the experimental measurements well for the first few femtoseconds, but then they start to diverge. And that divergence is what excites the scientists most, because when prediction and measurement do not agree, that is when you have found something you did not know ahead of time. As the Veritasium team notes, they animate electrons in practically every video they make. The fact that we can now actually see these electron densities moving around molecules feels nothing short of spectacular. Key takeaways. Edgerton's strobe, invented in the 1930s, still produces sharper single-frame images than modern high-speed cameras by trading temporal resolution for spatial resolution. A strobe powerful enough to illuminate the ground from a mile up helped photograph Normandy the night before D-Day. Single-pixel cameras that count photons a trillion times per second can film light propagating through a scene by repeating the same experiment for each pixel position. At SLAC, relativistic electrons produce attosecond X-ray pulses that serve as molecular-scale strobes, enabling movies of electron density changes inside molecules at a quadrillion frames per second. The technology spans a century, from curiosity about electric motors to visualizing the quantum behavior of electrons, all connected by the same fundamental idea: freeze time with a flash short enough to capture what the eye cannot see.